Section 22.20, Metal-metal bonding and metal clusters. Subsection A, structure of clusters. Now let's look at these two structures. In this structure, there are metal-metal bonds between cobalt atoms. Over here, we have metal ligand, metal bridges. Subsection B, electron counting in clusters. So when you have two metal bonds, these two electrons can both be counted as valence electrons for each of the two involved transition metal atoms. So I'm going to give you an example here. A neutral cobalt atom has a total of 9 valence electrons. And then we have 6 sigma bonding electrons from these 3 carbonyl ligands. So 9 plus 6, 15. However, it's not just 15, it's 18. This is because this cobalt and this cobalt share 2 electrons in this single bond. One electron comes from this cobalt, the other electron comes from this cobalt. However, both electrons can be counted for this cobalt and also for this cobalt. So in that sense, we use this cobalt to form 3 single bonds here, and it uses 1, 2, 3. It uses 3 electrons of its own, but at the same time, it actually gets 3 more electrons from the 3 other cobalt atoms. So if you look at this 3 single bonds, there are 6 electrons. 6 electrons. Then this cobalt has still 6 d electrons unused. So 6 plus 6 plus 6, that's 18 electron structure for this cobalt. Another example is this. This is much simpler. There's a single bond between these 2 manganese transition metal centers. This single bond consists of 2 electrons. One comes from each of the 2 manganese. And then, therefore, each manganese atom has a total of 7 valence electrons. In that case, well, they use only 1 to form a single bond between each other. 6 more d electrons left, 6 d electrons. And then 5 carbonyl ligands on each manganese, that's 10 electrons. So 6 plus 10, that's 16. And then don't forget about the bond between the 2 manganese atoms. That's another 2 valence electrons. So in this case, each manganese is also surrounded by 18 valence electrons. Although the total number of valence electrons surrounding these 2 transition metals is only 34. Again, these 2 transition metals share 2 electrons. Subsection C, isolable analogies. 2 fragments are isolable if their frontier orbitals have the same symmetry. We're talking about sigma, pi, or delta symmetry, and also they need to have similar energies and similar electron occupation. So that means their frontier orbitals will behave similarly in chemical reactions. Let me give you a few examples. 1, 2, 3, 4. These 4 are isolable. Again, isolable means over here frontier orbitals have the same symmetry, same energies, and the same electron occupation. It's easier to judge whether 2 fragments have frontier orbitals with same symmetry and or same electron occupation, but orbital energies. Well, you probably will have to do some quantum mechanical calculations. 1, 2, 3, 4. At least they have similar shapes, similar symmetry. 2 lobes, 2 lobes, 2 lobes, 2 lobes, 2 lobes. Over here, we're looking at C2V point group. Okay, 1, 2, 3, 4, 5. These 5 examples all belong to this C2V point group. And if you look at the shapes of these 2 lobes, they are similar to each other. So these 5 examples are isolable. Over here, okay, 1, 2, 3, okay, 6 examples as well. This 6 examples belong to the C3V point group, and each of them has 3 lobes. Okay, so these 6 are also isolable. Isolable ligands or complexes behave similarly in their chemical properties. Subsection D, synthesis of clusters. We can make clusters by doing thermal expulsion, condensation of metal carbonyl anion and a neutral complex, condensation of an unsaturated complex and another complex, etc., etc. Here are a few examples. Over here, you have two of these complexes, okay, and then they can remove 4 monoxide, okay, carbonyl ligands, and form a larger cluster here. So I showed you the structure of this cluster before. I think it's right here. Okay, 4 cobalt, 12 carbonyl ligands. Condensation of a metal carbonyl anion and the neutral complex. This is the anion, this is neutral. This itself is a cluster, but it can become bigger by, bonding to another tetracarbonyl nickel, and then 4 CO are removed from this bigger cluster, okay, over here. Condensation of an unsaturated complex and another complex. This looks a little complicated, but you just need to focus on this double bond here. So really, this double bond may interact with this transition metal center. So that's it. And then you have 1, 2, 3 membered rings here. Okay, this comes from that double bond, and this double bond interact with this PT. And on the reactant side, you have 2 this COD ligands bonded to platinum, and over here only 1 COD bonded to platinum. What's COD? This is COD. COD is 1,5-cyclooctadiene. So each COD may form 2 bonds with platinum. So over here, if you just focus on the 4 bonds surrounding platinum, it's actually square planar. Again, it's very common to find 4D8 or 5D8 transition metal centers in a square planar structure. So it's roughly square planar, okay, because this is clearly not 90 degrees, but still it's roughly a square planar structure.